Now, to fully describe the uncertainty in something, we need the full probability distribution function. But that's complicated and hard to explain and hard to compute. Often it's nice if we could put a much simpler number or two to the uncertainty in something, and usually that's enough. Now, there are three different ways we could do this. One way is the range. By range, we're simply saying we give the highest possible value something could have and the lowest possible value. So let's imagine, for example, that we say the rain tomorrow is going to be between 2 and 8 millimeters. That tells us the rain will always be between 2 and 8 millimeters. It will never be 1.5, never be 8.3. Now that works if your probability distribution function looks something like this. Right, that's 2 and that's 8 millimeters of rain. So it's got sharp edges down here and down there, and it's 0 outside. In that case, you really can say it'll always be within that range. The trouble is, probability distribution functions like this are really not very common. Much more common probability distribution functions look a bit more like a normal distribution. And the trouble with them is they don't have sharp edges. The probability is much lower away from the mean, but there's still a small probability right out here. So technically speaking, the range for that is going to be between minus infinity and plus infinity. So you say, the rain, well, in the case of rain, it can't be negative, I guess, so the rain would have to be 0 to plus infinity. If you said that in the weather forecast, it's not very helpful. So range isn't useful because normally there will be a tail to the distribution. It won't quite cut off to edge, and so you can, with a very low probability, get extreme values. The only situation in which a range really is useful would be if there's some sort of specification and testing. So let's say you're building metal bolts and you want to guarantee they're all between 10 and 10.1 millimeters in length. And what might happen at the factory is you make them with a uncertainty that looks something like a bell curve, a normal distribution, but then you test them all, and if they don't meet specification, you throw them away. So that might give sharp edges to your distribution and might give you something like this where the range is useful. But by and large, the range is not useful. However, it is what most people interpret uncertainties as meaning. So normally if you say, I think the range is going to be 2 to 8 millimeters, people think it'll definitely be in that range. And that's not wise. So that leads us to the second and rather better way to describe uncertainties, which is confidence intervals. The idea here is you say, instead of saying, here is the range that we're 100% certain the data will be in, we'd say, here is the range where we are, for example, 95% certain. So we can say that the rainfall tomorrow is going to be between 2 and 8 millimeters of rain with 95% confidence. Now that's better because what it does is you can take your probability distribution function and pick a value which contains 95% of the area. So maybe 5% of the area is down here on this wing and that wing, but 95% is in the middle. So this range, you're 95% confident that the data will lie within it. So you might say, global warming will increase sea levels by 2100 AD by between 0.2 and 1.3 meters with 95% confidence. So that's a much better way of dealing with the fact there's a little tail at both ends, while still giving some useful information. This is in fact what most actual researchers, at least in astrophysics, do these days. So I think it's arguably the best way to describe these things because it's very clear and explicit. It would confuse politicians if you said something like this, like we think the growth rate of the economy is going to be between 1 and 3% with 95% confidence. But politicians are easily confused. However, this is not the most common method of explaining things. The most common is what's called the standard uncertainty. What is standard uncertainty? Well, this is actually mandated there is a confederation of international measurement labs. Most countries have a measurement lab which is responsible for defining the weight and height and length scales for all measurements so that you can make sure that a shop is selling you the right weight or height or temperature of whatever it is. And these labs have all got together to come up with the GUM, the Guide to the Expression of Uncertainties in Measurement, which is an international standard. So they've all agreed to use the same way to express uncertainties, and we will do the same in this course for consistency, just so that everyone can understand everybody else. It's not to say it's the best way, but it's a consistent standard. And this defines the standard uncertainty. And the standard uncertainty is what you get if you make large numbers of repeat measurements and you measure the standard deviation of all the repeat measurements. It's the same as the sigma in the equation we saw for the normal curve. And that is actually the standard. We'll come back to what it actually means in practice. But roughly speaking, it corresponds to a 68% confidence interval. If it's a normal distribution, 68% of the data points will lie within it.